Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Asia binti Ismail. My matric number is DE210102. I am from Group 5, Section 1. So in today's video, our group will be doing a demonstration for Lab Power System Part B, which is modeling of transmission line. So let's proceed to the first exercise of the experiment, which is short transmission line. So the question states the 220 kilovolt three-phase transmission line is 40 km long. The resistance per phase is 0.15 ohm per kilometer and the inductance per phase is 1.3623 millihenry per kilometer. The shunt capacitance is negligible. Use the short line model to find the voltage and power at the sending end and the voltage regulation and efficiency when the line supplying a three-phase load of A 381 megawatt at 0.8 power factor lagging at 220 kilovolt. And second, to find the voltage regulation and efficiency for 381 megawatt at 0.8 power factor leading at 220 kilovolt. So this is the program or the coding for the MATLAB. So I have copied the coding and paste it in the MATLAB. So let's take a look. And the first line is VRLL, which is the 220 kilovolt. And then the second line is we need to find the receiving end voltage per phase, and then also we need to find the series impedance per phase. And then after we have calculate the receiving end voltage per phase and series impedance per phase, we can then proceed to find the voltage regulation and the transmission line efficiency for the first question, which is for 0.8 power factor lagging. So this is the coding. We need to find the apparent power, the current per phase, the sending end voltage, sending end to end line voltage magnitude, sending end power, voltage regulation. So this is the part where we want to calculate in this execution of MATLAB coding, which is the regulation, REG, voltage regulation in percentage, and also the efficiency of transmission line also in percentage. And then we proceed to the second question, which is to find the voltage regulation and transmission line efficiency for 0.8 power factor leading. Okay, the formula is exactly the same, except for certain part they are a little bit different. And then also for this second question, which is B, we also need to find the voltage regulation and also the efficiency of the transmission line. So after we have finished writing the coding for the MATLAB, then we can save and then run the simulation. Okay, so here we can see for the first question, which is A, for 0.8 power factor lagging, we can see the VSLL value, the SS value, and then the voltage regulation, and also the efficiency for the 0.8 power factor lagging. So in this, from the execution of this MATLAB coding, we can see the voltage regulation for 0.8 power factor lagging is 13.6448%, and also the transmission line for this 0.8 power factor lagging is 94.4252%. And as for the question B, which is for 0.8 power factor leading, we can see the voltage regulation is equal to negative 4.4144%, and also the transmission line efficiency is equal to 94.4252%. So how we can know whether the display value here is correct or not? We can compare it to the manual calculation. So we can see here. Okay, this is for the first part, which is for 0.8 power factor lagging, the voltage regulation is percent VR is equal to 13.6%. Okay, we can see here it's the same. And also for the transmission line efficiency is 94.4%. And as compared to the MATLAB execution, you can see it's also the same. And for part B, we can see the voltage regulation is equal to negative 4.4144%. And from the manual calculation is negative 4.40%, and the transmission line efficiency for manual calculation is 94.4%. And as for the execution, from the execution of MATLAB coding, we can see also the same, which is 94.4252%. So I think that's all for exercise short transmission line. Then we will proceed to the second exercise, which is the medium transmission line. That's all from me.
Alright, so this is the coding for medium transmission line. The coding is stated in the left sheet, and then we run, and we enter the length of line, which is 200, and enter the receiving voltage, which is 132, since it's kilovolt. So kilo is 10 to the power of 3, enter. The power is 50 megawatt. Mega is 10 to the power of 6, and power factor is 0.8. Enter the R per phase per kilometer, which is 0.16, as stated in the question. The space 1 is 4, space 2 is 5, space 3 is 6. Then we enter, and then it is shown a value of A constant, B constant, C constant, D and D constant. So the inductor is negative 20.3102. The capacitor is 0.003903. The voltage regulation is 220.347653, and the efficiency is 18.631597. That's all from me. Thank you.
Good day to everyone. My name is Tarmiganda Chanalaki Nadrasan, and my matrix ID is DE220110. So today, for the lab modeling of transmission line part B, the task I have been given is this exercise 1, which I have to form the Y bus matrix from the given data below. So using this data that is given and the example of the coding which is given in the lab, I have to form the Y bus matrix. So what I did was I used this codings and replaced it with the proper values and then calculated and formed the Y bus matrix. So let me explain what I did with what are the changes I did in the coding itself. So the B and the S are the number of buses and the number of impedances. So B equals to 3 and S equals to 3. So where we get this value is through here. So you can see is the starting buses are there are 3 buses here. And the impedance are there are 3 impedance series line impedance here. That's why it's 3. And then SB, the starting bus would be 1, 2, and 3, and the receiving bus would be 2, 3, and 1. Where it is shown here. As you can see here, the starting bus are 1, 2, 3. The receiving bus can be seen in the ending bus here. It's like starting from 1 to 2, 2 to 3, and then 3 to 1. That's how it works. And then for the Z, these are the series line impedance, which are already given in the table just now. And then Y is the line charging impedance. So let me go through the codings, the calculation part of the coding briefly. So as you can see, K1 would be the starting bus, and then K2 would be the receiving bus. And then ADM, this is a 1 over Z. ADM is a formula where 1 over Z, where we divide the series line impedance by 1. And as you can see here in this formula here, it is shown that K1 is the starting bus for that impedance, and Y is the line charging impedance for that impedance. And then for this as well, same as just like that, where K2 is the receiving bus for that impedance, and Y is the line charging impedance for that impedance. In this formula here, Y bus K1, K2 equals to negative EDM. It is where K1 is the starting bus, and for that impedance, K2 is the receiving bus for that impedance. And then here, it's just like that, where K2 is the receiving bus for that impedance, and K1 is the starting bus for that impedance. So what these are the changes I did in the, not changes, these are the values that I put into the codings given. So how to form the Y bus matrix? We just have to copy this edited formula, the edited codings, and put it in the command window here. Just copy paste and enter. So this is the Y bus matrix, the results. So as you can see, this matrix is a complex symmetric matrix of size of 3 by 3 as expected for a 3 bus system. So we can conclude that this Y bus matrix is used to represent the admittance of a power system, and it's important for analyzing the power flow in the system. The code just now we use is a standard formula for calculating the Y bus matrix, which involves adding the series impedance and the line charging admittance to the diagonal elements of the corresponding buses, and adding the negative of the admittance to the off diagonal elements. That's all from me. Thank you.